Okay, so PigTails today, there are a few videos, short videos here, the truth about pigtails, how to make electrical pigtail, and so on, how to choose. Now, I'm going to ask you to watch that on your own. Here are the links, and well, that's going to give you a little bit more understanding on what the pigtails are all about. However, in short, why do we need to know how to install pigtails? Well, let's see here. We have a situation. Zoom. All right, so we have few wires that need to be joined together, and they need to be connected to whatever screw terminal. So here we have a bunch of like 1, 2, 3 neutral wires. Of course, we're not going to twist them into a braid, and that braid is not going to be connected to one screw terminal. We need one wire to be connected to the screw terminal. So we're going to make something that's called a pigtail. Make a braid, join them all together, and then carry one extra wire out of that one, and that wire is going to be connected to the screw terminal. So in this case, 1, 2, 3 screw terminals are connected in this way from this device box. Okay. Another reason why you would want to make a pigtail is sometimes when you get into sometimes you might find yourself in a situation that the wires in the device box were worked on so many times, and every time somebody in the past would go at it, they would make those shorter and shorter and shorter, and after a while, even though it's just one wire that you need to connect, it's just too short. So you're going to just strip a piece of that wire, get another longer wire, make a braided connection or braided junction, stick a wire knot on this thing, or a twist-on connector, or moret, depending on what it is, who made it. And that way you can extend this connection into some sort of a comfortable length that you can actually connect into well, whatever terminal you need to connect this. Another reason yet that you would need to make a pigtail is to join wires that are supposed to be connected into any device in the device box, but maybe pass through the box and continue on. The way we are installing things is that we have a bunch of device boxes or raceways installed in the building, especially if it's a new installation. And then we're going to run wires from the device box that is somewhere on the wall or in the ceiling, and maybe the other wire goes into some sort of a receptacle device box that is in the wall. So we're going to pull the length from the device box right into the junction box, and we're not going to, if this wire has to pass through and go somewhere else, we're not going to pull extra length here and run the slack and continue into another knockout and bring it out into wherever it has to go. Well, you can do that if you really want to, but generally this thing is not being done because if it's a bigger project and you have a lot of those, then this job would take you pretty much forever. You'll never be able to be done in some sort of a civilized time manner. Okay. So in order to make things nicely structurally sound, systematic, pull the wire, cut the length, leave it, pull the wire, cut the length, cut. So all the wires are being pulled, and then the wires are going to be joined. Of course, the wires have to be labeled as they are being pulled into the device boxes and into the raceways, such as, for example, EMT. Okay. Which is electrical metallic tubing, which generally we call into the pipes. All right. So that's the couple reasons or few reasons that I was able to give you, and maybe there's some other reasons, but who knows, right? But get the general idea of what's going on. Now, as far as trying to figure out what colors and what size is it, but what does it mean size? There's no unit for for the wire nut or twist on connector. How do you establish a size? Some people say, okay, here's the orange ones, here's the red ones, so the black ones are bigger than the orange ones, and maybe there's small blue ones or gray ones, blah blah blah. There's no standardization as far as coloring of those wire nuts. Different companies make, okay, before it was pretty much one company that we used to make those twist-on connectors, and the company was called Moret. So that's why quite often you're going to hear the terminology such as Morets. These are the Morets, because Moret was the company the only one that was making it, right? And if the bits and pieces or the twist-on connectors, if they were made by just one company, and if that company would have its own standard as far as the colors and the sizes, then yes, you could sort of make some sort of a systematic sense out of that one. But now everybody and their brother is making those, and they're having the different colors, so you can't just go by the color and the size of it. You're going to find different colors, different shapes of those. So, forget trying to figure out the size of it and the color. What we need to go by is, we need to go by the box or the specifications when you buy those things. By those things, I mean the wire nuts or twist-on connectors. And on the box, you're going to find out how you can use that as far as how much wire you can pack into one of those. All right, so there would be stickers on the box. And this one says one size fits all. Well, I wouldn't trust that. Twist on wiring on connectors by Ideal. Yes, this one says one size fits all, but there's an asterisk. There's some asterisks here. So, well, what does that mean? Okay, so it says one size fits all, but, okay, and then you're going to have to find out what the but is. Now, as far as the anatomy of that, it would have a plastic or some sort of a PVC non-conductive housing, and you would have a conical shape type of a thread. Like this part here is threaded, and it's threaded in the clockwise direction. So when you want to tighten this wire nut around the wires, you're going to have to turn this clockwise in order to make a proper connection. Which brings me to the point that right here, this here has to be twisted, and it has to be twisted the right way. It has to be twisted with the same direction that the wire nut would turn in order to tighten its connection around these wires. If you twist these wires backwards, and you're going to try to connect the wire nut onto it, you will, by screwing this wire nut on, you will try to undo the twist action here, and it's just going to make a mess. Right? Also, notice when we prepare the wire nut, the wires for connections with this type of connection, we need, after the twisting the conductors, the stripped conductors, we need to trim them, and we need to trim them nice and square, not under an angle one way or the other, nice and square. They have to be trimmed. There cannot be any of those wires longer than the others, because this thing can protrude through the housing here, because the thread is going to grab onto the main body of the wires or the conductors, and if there is something that's sticking out here, it's going to poke through the housing, and we're going. In that case, we would have a situation when this whole connection would have an exposed copper, which could lead us to some situation that would be not good, because that can connect, make contact with other things that are in the box, okay, or maybe with the box itself. And if this connection is a hot wire or hot connection, and then there's a chance that this would touch maybe the box, which is connected to the ground, and boom, we have a situation that we don't want, right? So now I'm going to repeat what I said during the lab. Pre-twist or not to pre-twist? That is the question. If you look at this thing here, here's another visual on how things are being connected inside the wire nut. The thread grabs the conductors, and the thread should make physical contact with all the conductors that are participating in this whole exercise. Right? Also, we should not have anything protruding through the front of the housing here, and we should not have any exposed copper that would be beyond what the plastic housing would cover. In short, there should be not any exposed conductive areas for the obvious reasons, because they can touch some other things, and electricity through contact, physical contact, it would travel through in a way that is unwanted. So, pre-twist or not to pre-twist? Let me just get where's my board? Right here. All right. So, there is no code regulations whether you should pre-twist or not pre-twist. You need to make a connection that is safe. However, I'm just going to use common sense because I belong to the group of people that actually think that the connections should be pre-twisted, whether the sticker on the box of the connectors says, sometimes it says not pre-twisting, no pre-twisting necessary. Well, here's the situation. Okay, grab my pencil. If we have 3 conductors, 1, 2, and 3, all right. Let's say this is the thread of the, if we install the wire nut on it, the thread is going to be able to make physical contact with all 3 wires. We're talking about the situation that we don't pre-twist. We just put those wires all just beside each other, just like 3 wires here, and that's it. All right, and we're going to put the wire nut onto that. Okay. All right, so if we're looking at this thing from this angle here, we would see something like this. So if it's up to 3 wires, 3 conductors, yes, the wire nut thread is going to be able to make contact with all 3 wires. Right? What if we have more than 3 wires? We would have a situation like this. Here, here. Let's say we got 4 wires or 5 wires here. Now, what happens if we don't pre-twist? Then the thread would make contact with, the thread would be able to make contact with this area here, this area here, this area here, and this. What about this wire right here? This one right there. This wire will be held just by the compressive sort of action, by those 4 wires squeezing it inside. So we just have a squeezed wire that is between those other wires, with no making physical contact with the thread. And in my opinion, that could lead into some sort of unwanted situation because, as I always say, when you make those connections, you don't go there every 2 weeks and check them. You make that connection, you pack it in the box, and you leave it there. And sometimes it's there for like 20, 30 years. Nobody goes at it. Well, what happens is that temperatures go up and down. The connection could warm up or cool down depending on how much current there goes through it and so on. And if it's some sort of a sloppy connection or sloppy enough, then if some wires are just held by compression, there is a slight chance that it could wiggle itself out of the connection, or not necessarily wiggle itself out so it's actually going to fall out the whole junction or the whole connection, but it's going to make a contact that doesn't have enough pressure on contact. And then that could lead to oxidization. Oxidization could lead to more resistance. More resistance could lead to more resistance on contact, and the resistance on contact can lead to more heat, and that could lead to more oxidation, and the vicious circle just continues. And for the most part, if you're just plugging in just like a desk lamp or a clock radio or a TV even, it might not be an issue as far as something actually happening, some disastrous thing happening. However, maybe somebody decides later on, maybe after 15 years or something like that, somebody is going to decide to plug in an electric heater, which is going to draw way more power than the TV would. And then that amount of current that would still be within the circuit breaker ampacity. However, it can lead into some sort of well, not some sort of, but actually it can lead into a fire. So as far as pre-twist or not to pre-twist, here's my take on that. Make of it what you will. All right. When you later on you're out there in the field. Right. As I say again, nothing happens until something happens, and if something happens, then you're going to have all bunch of authorities and inspectors and whatnot breathing down your neck. Well, I can say that on a public forum. It's just the way it is, that the probability of everybody trying to make it look like it's your fault. It might be if you do a poor connection, or even if it's not. Humanity works that way, that trying to point fingers, trying to blame somebody else for whatever it is, just so we are not being blamed. It's our human nature. So, you know what, guess what? You're the last one who touched it. And make sure the connection that you make is actually pretty good. All right. Here's an example of a box. This is one of the boxes. I just took a picture of what we had in our lab. This is actually our lab. It's a different room that we used to have. However, it's from our school. Here's a sticker that explains, has a bit of an explanation of how to use this particular connector that is being sold. All right, so well, here's some kind of an asterisk listed as pressure type wire connector for use on solid and or stranded wire combinations. I do have a slight problem with that. Personally, if you have done any of those in the past, of those connections, you probably would know how much of a struggle it is to combine solid and stranded wire into that type of a connection. It is not the ideal situation, right? So there are other ways of handling that sometimes. Like for example, the relatively new, excuse me, WAGO connectors. That could be the solution, right? There are different opinions by different tradesmen, different individuals on how WAGO connectors work or not. Are they good or not? Well, they're approved, and if they're installed in the proper way, yes, they can be, especially when you're combining solid and a stranded wire. I would think that this would be a better way of making a connection than with the wire nut. All right, but now we're concentrating on the twist-on connectors. All right, so here is a little, I would say, legend on how this should be. This particular connector that's in the box with this sticker on should be installed. All right, so it says listed as a pressure type wire connector and solid and stranded wire combinations. And they give you a bit of a minimum and maximum combinations. Minimum is because if you don't put enough wire, enough meat on the bones, I would say, if you don't have the connection thick enough for the thread to grab on comfortably, then the thread will not be able to grab onto that braid that you make, and you're not going to have a solid connection. Maximum is how much can you pack into that before it's too much for this connector to handle. Right? So there's certain there's certain gap or span that we should fit ourselves within. All right, so in combinations of three. Okay, so 3 conductors of 22 gauge. See that? That's how we read this one. And maximum, so minimum of 3 connectors of 22 gauge. And 22 gauge is a thin wire. And maximum of 3 number 10 connections. And it says here, and most applications in between, including. And here are some examples that you could be okay. 1 to 3 of number 12 gauge. So you can have one 12 gauge wire, and you can cap it with the one of those. Right? Why would we want to put a connector on one wire? We're not connecting it to anything. Well, to prevent the wire from touching other wires, right? Or other things. Right? So minimum 1 to 3 of number 12 gauge, and maximum of 4 of 12 connectors, and here's solid only. All right, so one, okay, and you can see 4 14 gauges with 2 number 16 gauges. All right, and so that's how you could determine. However, you should know also that if you're struggling with this connection, like for example, you're trying to put that wire nut on or twist-on connector on, and it's not grabbing, then you don't have enough wire in there. All right. So obviously that would not be a safe connection. Or if there are too many wires, and you're trying to put that on, and the thread has a physical difficulty with grabbing all those connectors and holding them in one place, then obviously you have too much wires in there. So choose different connector, bigger one. And here's the whole thing in French because we're in Canada. Right? So I'm going to leave you with this one here when it comes to, we're not done yet with the class. Don't forget to watch those videos. This presentation will be available in about half an hour. This is what today is, March 11, 2024. And we have 9:30 almost in the morning. Okay, so that's in case somebody's wondering when this thing was recorded, when they're watching this video later. All right, so that's as far as the pigtails. Now, we're going to use the pigtails. Actually, we're going to, in this lab that's coming on this week, and I think some of the groups are having it today with Mr. Cunningham, if I'm not mistaken. Excuse me. We're going to put all the knowledge that we have gained together into one sort of project, because we can't call it project really. It's still a lab exercise. All right, so I'm going to explain to you what we're going to do. So we're going to use our knowledge that we gained from making a proper screw terminal connection, making a proper pigtail, connecting EMT into the boxes, and well, need to make the whole thing work. All right, I have heard that you have already been exposed to the idea of a three-way switch, but let's just do a bit of a review on how the whole three-way switch works. All right, here we have, I used a multi-sim, and I put some devices, some components onto the multi-sim in order to give the idea of how is it that the three-way switch works. All right, now what do we have here? We have a power supply. Doesn't matter what it is, it's just 5-volt power supply DC. Of course, in the reality, when it comes to electrical installations in North America, well, what we have in the wall is we have 120 volts AC RMS. But we're not concerned with that now. We're just going to analyze the logic of not the signal, logic of the current flow in a three-way switch. Where do we use three-way switch as a reminder? Well, this is sometimes it's called stairway or stairwell switch. Stairway switch. We have one light in the basement, and you have one switch in the bottom of the stairs, and you have one switch on the top of the stairs, and you can control the light from either or of those switches individually. That's pretty cool, right? So how is it, how does this thing work? Well, the three-way switch, of course, is a three-way switch because there are three ways of getting into the switch. Number 1, number 2, number 3. So here is a common switch because you see here, that's how it works. This one is a common terminal, and these two are called travelers. It's a single pole double throw. Single pole, we can throw it two ways. Single pole double throw. I'm just operating that thing now. Okay. All right. Now, if you want to find out which terminal is which, there's an easy way, because if they are labeled on the switches that you buy, but let's say they were not labeled. How would you find out which are the travelers and which is the common? Well, let's get a multimeter here. Okay, and we're going to set up the multimeter. I just double clicked on that. We're going to set this up as an ohm meter. Okay, so we have an ohm meter. So here's our display of our multimeter. All right. Let's connect. Let's make some connections. Connect that to one of the travelers, connect the other terminal to the common, and let's say here, start the simulation. Let's see what we're going to have on the display. Boom. All right. Well, we have 99.992 mega ohms. Well, that's pretty much almost the resistance of the air, or maybe close to that. Which means we have an open circuit. See here, if we disconnect that line here, it's not connected to anything. Start simulation again, we're going to get the same thing. Well, no, it's just open. Okay, that's how it works. This thing is trying to simulate more than it is. Connect that. Well, maybe they're trying to simulate the resistance of the dust within. All right. This thing is high, so let's just say this thing, it's an open circuit. Now, what happens if we close? Boom. Oh, between here and here we have 0 ohms, 0 resistance. Okay, no resistance. Of course, we have a connection. Okay. All right. What happens if we connect the line to the other one, the other traveler? There. Start simulation. All right. Here we have an open circuit. Close the switch the other way or flip it. Oh, we have 0 ohms now. See down here? All right. Now we have 0 ohms. Okay, so we can make a connect. We can gonna get reading like this. All right. Now what happens if we connect the ohm meter into the travelers? Start simulation. We have an open circuit. Is anything going to change if we flip the switch? Of course not, because these two will never be connected. Well, so if you just keep poking around the screw terminals, of course it has to be out of the circuit with an ohm meter. If you have those two terminals that no matter which way you flip the switch, there's not going to be any reaction from the meter. It's going to have an open circuit. Excuse me. Then these two are travelers, just like the travelers around the world. Traveler. Okay. All right. So here's a bit of a visual on that. Okay, now let me just get rid of that. All right, how do we make a connection? How are we standing with time? We're good. We're good. All right, so here's the power supply. We have two three-way switches here. We have a light, and we do have a ground, which are not going to connect, but it has to be within the proximity for this thing to work. All right, so first things first. Connect the travelers, all right? Traveler to traveler. Done, okay? And then we're going to come in to the common and out of the common, all right? So go to in on one of the commons and out of the common into the load. And of course, we have to close the circuit because the light bulb is never going to be on if the circuit is not complete. A current has to have a closed loop. It has to have a return path. It has to have somewhere to flow. All right. So we're going to provide a return path right to the power supply. All right. Let's see if we have. Is this light bulb going to be on or off? Okay. Well, okay. Do we have a closed path, closed loop? We leave through one of the terminals, see if we can find our way into the other one. Okay, we travel there here. Okay, boom. Okay, then we go through that here. All right, we make a connection here. Oops, that's where things stop. There is no closed loop. The current doesn't have anywhere to go because the bridge is destroyed. There is no bridge here, and there's a river. Right. All right. What happens if we flip one of those switches? Oh, do we have a closed circuit? Travel here, travel here, travel here, through the load, return. Okay, right. Now, if we open this one here, travel here, whoops, we fell off the wagon right here, right? There's no closed circuit here, no closed loop. Okay, let's start the simulation and see if the light bulb is on. Okay, simulation is on. Light bulb is not on. Of course it's not, because there is no, as soon as we open, there's no closed loop. There's no closed circuit. Let's see if we can flip any of those switches. Oh, I'm not sure if you can see it on video. This thing just turned yellow. Okay, that means the light bulb is on. Of course. What do we do this here? All right, we'll just turn that thing off. Oh, we do this here. Oh, all right. So that's how it works. Okay. Now, this is going to be part of the assignment, so listen carefully, right? What happens if we have, because you're not going to always have this kind of situation when you're going to have power supply, first switch, second switch, and the light and the load at the end of the run. Sometimes you're going to have the load in the middle of the run, like here, And sometimes you're going to have the load at the end of at the beginning of the run. All right, let's see. Same logic or same idea. Okay. All right. Remember what we did first? First, connect the travelers, then into the one of the commons, out of the commons through the load, and come back. All right. Let's see here. Connect the travelers. Am I stopped? Okay. Connect the travelers. Okay. And then we're going to come into the common and out of the common. Okay, so into the common here, out of the common, and come back here. All right, so this would be a device box. All right, this would be a device box. No, not here. This would be a device box, and this would be a device box. All right, and in between there will be pipes. All right, so can we make it work? Let's see here. Flip. Oh, look at that. The current flows through here, through the switch, through another switch, through the load, and has a way to return. If we flip any of those switches, we are breaking the pathway of the current. All right, see? All right. Now let's take a third scenario here with the light bulb or load at the beginning of the run. All right. Same thing. What do we do? Connect the travelers from the power supply into one of the commons and from the other common into the load, through the load, and come back. All right. Connect the travelers. Here. Here. All right. We're going to go through the device box with the light bulb and maybe connect this to the first common. And out of the second common, we're going to connect that through the light bulb, and kaboom, we have a thing. So this would be a device box. This would be a device box with the switch, and this would be another device box with another switch, and in between there would be pipes. Is this going to work? Well, let's find out. Start the simulation. Oh, we already have. Start the simulation. Light bulb is not on because there's no closed loop. Yeah, we're coming from here, going through the switch. Whoops, that's where the pathway stops. Okay, let's make a bridge. Boom. All right, here. There we go. Let's bring this bridge down. Whoops, there we go. No return pathway for the current. Well, let's close that one now here. Okay. So that's how this. Now, notice one thing. I'm going to point something to you. In all the situations, all the cases, all the connections here, there is a direct connection to the. Let's say this is the neutral. This is the hot. See here, the positive is the hot. The negative is the neutral. Of course, in AC situation, we're going to have the neutral and hot. Okay, there's no positive and negative. Now the ground is going to be connected to the device box. Right. And so on in all three situations. The ground is going to be connected to the device box. That's a bad kind of all right. Of course, internally through the electrical panel, those two are going to be connected, which would look like this. All right. Notice that when the load is connected, it has a direct connection that is uninterrupted wire only to the neutral. We never have, we're never supposed to have the any of the terminals in the load device box directly connected to hot. So yes, we do have this one hot. Is provided from one side of the load and the other side is directly connected to the neutral. This one here, this wire is called a switched hot because the hot is being switched on and off. See? Oh. Okay. So if we turn off the switch and if the light is off, we should have no connection between this wire and the hot. Is it true? Of course it is true. We go here through this switch and that's where the connection falls off. It's not being connected to anything. So for safety, that's for safety reasons. And of course, in order to be legal, we need to do that. Also, I'm pretty sure the other class that I'm not sure who it was, who you have this thing with, but somebody told me that you already were introduced to the idea of the three switch. Just in case, I'm pretty sure you were told that. Right now, according to CEC, Canadian Electrical Code, and I don't have the paragraph here with me because I'm not teaching code. You get a code professor with a code class. However, I know someone who teaches code and he told me a thing or two. And what we're supposed to have is have to make sure that the neutral wire is with every device box. The neutral wire. So do we have a neutral wire in this box? Yes. Do we have a neutral wire in this box? Yes. Do we have a neutral wire in? No. So what we need to do is we just need to make sure. I wonder if I can do this. We have to make sure that the neutral wire goes everywhere into every device box. So now, do we have a neutral in this device box? Yes. Do we have a neutral direct connection to the neutral in this box? Yes. Do we have a neutral in this box? Yes. Is this neutral being connected to anything? Doesn't matter, it has to be there. Okay, that's all. Same thing with here. Do we have that everywhere? Do we have a neutral here? Well, yes, it's this one, right? Do we have a neutral here? No. And we don't have a neutral here as well. So what we're supposed to do is, fortunately, this is the way I have to do it. I'm just going to run the wire all the way to the last box. And this one here goes back to here. And this one goes back to here. All right. So now do we have a neutral in this box? Yes. Make it look better here. There we go. Do we have a neutral wire in this box? Yes. It's not connected to any of the devices, but we still have to have there. It's the code. Do we have a neutral here? Yes. And of course, this would be the one wire that we would put a wire knot on just to cap it, making sure that nothing is going to be touching this wire or this wire touching anything else. All right, now, how are we going to, let's say this is a device box, so the wire is passing through it. Can you just pull the wire right through? Yes, but you're not going to do that. You're going to pull the wire from wherever it's pulled, leave it here. From here, pull it here, leave it there. From here, pull it here, leave it there. So you're going to have two unconnected ends here to one. You make a pigtail, shove it in the box. Make a pigtail, shove it in the box, leave it there, right? So that's why we practiced making pigtails. We are putting all the stuff that we have learned so far in all the labs into one sort of exercise. You should have no problem. You should be comfortable with connecting all those things. How is it going to look in reality? Well, it is going to look somewhat like this. I'm going to switch pages here. All right, so we're going to have a device box. All right. We're going to have another device box. We're just looking at it from the side. And we're going to have another device box. It's a different device box. It's a lamp holder. Okay. Here's a utility box, and a lamp holder with a, well, we're going to have a light bulb right here. All right. Light bulb, all right, and this one here. In between those, we're going to have an EMT. There's going to be a pipe. We're going to make a short one. And there's going to be another pipe between here. Here's going to be an EMT connector. Here's going to be an EMT connector. We have used those. Here's going to be an EMT connector. And as well as here. And over here, we're going to have a 2-screw connector. We're going to get NMD90 wire, bring it here, and we're going to have hot, neutral, and grounding wire or bonding wire. So 3 out of there. We're going to strip it, all right? Then we're going to have a first switch, first 3-way switch, all right? And then there's going to be another 3-way switch that goes into here. What do we need? Remember? It's going to be the one with the load at the end of the run. What am I doing here? What did I just turn on? No, that's not what I want. No. Yeah. This one here. Remember? That's this situation that we have. Here's the first device box. Here's the second device box. Here's the third device box, which is the lamp holder. And in between, we're going to have pipes. So the wires have to be in the pipe. Yeah. So that's right here. So we're going to have, what, 2 travelers together. What do we need between these 2 boxes? Yeah. What do we need? And you know what? I'm going to have you connect this thing without looking at any diagrams. So you have to understand the concept of what's going on. Here. How many wires do we need between these 2 boxes? Well, we need to connect the travelers, and we need to pass through the neutral. So 3, right? 2 hot ones, 1 neutral. So one of them has to be white. The other ones have to be, well, hot wires. So it could be 2 black ones, 2 red ones, 1 black, 1 red, and so on. As long as we'll have 3 whites, right? So white is neutral. We connect the ground or the bond only to the first box if we are dealing with EMT, electrical metallic tubing, because this is electrical. If we connect the ground, let's say, all right, where's my eraser? Here's my eraser. Let's say I'm going to erase that wire right here. And that is going to go right to the ground, to the screw terminal, right there. Connect that. Of course, we're going to make it proper. I'm just, we're not going to connect just a straight run from here. See, that would be too short of a wire. Maybe I should just make it proper. Okay, so here we're going to go and connect it to the ground, for example. All right. And then we're going to have hot and neutral. Okay. So then we need to have more wires here. We need to have 3 wires to connect the travelers to travelers, and one into the common. All right. All right. So it's just here. I'm going to erase that. We're just going to go one by one. All right. All right. Travelers. We're going to connect the travelers. So we need 2 wires here, right? I should change. No, I should be fine. So between those 2 boxes, there's going to be a wire here going to one traveler and another wire going to another traveler. Of course, this part right here, this is inside the pipe, okay? I just can't fit that into, so these wires are in this pipe. So the travelers are connected. Then we're going to have the hat going into one of the commons. Right? I'm going to connect it to one of the commons of the switch. And then what else do we need? We need to connect the common into the hat of the light bulb. Okay, so we're going to have the common going through the pipe and coming out in the box, and it's going to connect into the hat part of the light bulb, and we're going to come back out of the neutral, and we're going to go, oops, I just touched the wire, I'm not supposed to. There, they're not touching. Okay, and they're going to come out over here. Okay. What else we need to provide? Okay, so we're going to get another wire coming in here. It's going to stick out here, and we have another neutral wire. I'm going to bring it up to here. So here we're going to install a wire nut. Here we're going to install a wire nut. And the other wire nuts here? No. All right. And this way we're going to have the three-way switch connected. So how many wires do we have in this? We have, well, switched hat. So going to be hat here, and neutral. Right. This is hat. And it's, of course, it's going to be switched hat. There is going to be, oops, come on, stay there. So this one is going to be switched hat, okay, neutral, and that's it. This is just a pipe here. I should erase probably those just to make sure that we're not confused. Eraser. Ay, ay, ay. We should have eraser on. Here is the eraser. Okay, so we're going to erase those wires. That's not a wire, it's a pipe, just so things are a little bit more clear. All right. Here, erase that pipe. All right. So here, and there's another pipe. No, there's no. So over here, we just have 3 wires here in the conduit. We're just going to mark it like this here. Here's another conduit here between these two. And that's going to be our lab. And over here, just so we know, we're going to have a NMD90. That's going to be this wire right here. And over here, we're going to have single conductors. Well, it's going to be easier if I just do this. Okay, and these were these here. So that's what we're going to do in our lab. That's the single conductors right here. And we're going to find means of connecting those device boxes to each other. All right, I can change the size of the brush. Yeah, thank you. Yeah. Easier by right click. Yeah, okay, thank you. All right. So that's it for today. I think we're, oh wow, a beer is gonna kill me. I think you have a class with her like right now. All right. Sorry to keep you a bit longer. Okay. I'll see you when I see you. Some of us are going to see Mr. Cunningham today, I think, and then through the rest of the week, we're going to continue with this very lab. And of course, I'm going to give you a demo. We're going to give you a demo before we put you to work on this thing. All right. Thank you, and have a good, well, almost Friday, which is Monday. Right. Goodbye.